Okay, so good evening, everyone. Uh, so welcome to this live session on uh, this Monday, uh, 5 p.m. So from this week onwards, we'll be having live sessions on Monday 5 to 6 p.m. and Wednesday 5 to 6 p.m. Is this informed, everyone? I hope there's no ambiguity in this. Okay, so from this week onwards, these are our sessions. Monday 5 to 6 p.m. and Wednesday 5 to 6 p.m. Okay, so in today's live session, so today and Wednesday, so this week, that is week 5 of the course. Okay, so what I'll do is I'll do the review of the course material today, and coming Wednesday's live session, I'll will do the problem session. So it means that whatever the doubts you have in the lecture material, so that to be clarified in this live session. If you are having any doubts, you can uh, ask me. So I'll quickly go through the course material, whatever the course material I have, professor has explained in the video. I'll quickly go through that. So if you're having any quick doubts, you can ask this 1 hour. And at the end of the 1 hour, we'll have a small surprise test also. Okay, so the lecture one covers basically the two topics. So basically, this lecture introduced the concept of the feedback control. It talks about the open
Sir,
loop.
I have one
Yeah.
question.
Yes.
In both Monday and Wednesday, we have surprise test. Both day
Yes.
or only one
Yes.
day?
Yes. Yes. We'll have a surprise test on every day, both the
Okay,
sessions. Okay.
okay, sir.
So assume that surprise test will be the material which we cover on that day itself. So that's why we conduct the test at the end of this live session.
Okay, okay, sir.
Okay. Yeah.
Okay, sir.
So basically, this lecture covers the concept of feedback control. So which covers open loop as well as the closed loop. So if you see this, when you design the controller for any system, so in general, so these are the four concepts which we see throughout the control system course: stability, tracking, regulation, and sensitivity. That we'll see in these four lectures now. So in this quick review. Okay, so first we'll start with this open loop control. So basically, when we start this course, we started with this open loop control where we have the plant and we have this controller. Okay, so let me reduce this and then I'll use the space. Okay, so they both are connected. The reference input R of S is given to the controller. Then controller will modify the signal and pass the control signal U of T. Okay, to the plant. In along with U of T, some disturbances shall be added to the control input. So we'll get the output here. So where this has the reference input and this is the final output. Where here, so the output has the reference input does not know anything about the output. So it means that we are not giving, we are not informing the reference input. This is the output every time we are getting. Okay. So there are disadvantages like what we give only the reference input and we are not, we don't care about what we are getting at the output. In general, most of the systems like traffic lights, the washing machines, etc. So they all comes under the open loop system. Okay, so mostly these open loop systems are they are heavily based on these disturbances shall be added after we calculate this control input. So it means that we give this reference input by expecting that we wanted to get something at the output, but in middle the disturbances shall be added. So obviously the output will be deviated from what we expected. So here in the open loop control, we have no control or we do no correction for the output we get because of this deviated output because of these disturbances. Suppose here you see this output. So how do we calculate that? So we multiply the controller with the reference, and then uh, that will be added with disturbance, multiply with the plant transfer function. We get this final output. Okay. So the error will be calculated as the reference output, reference input minus the actual output we get. So this is the expression. Okay. So for example, here, this is the same example Professor has explained throughout this entire week. So here this example says that we are dealing with thermal control system, where that a thermal control system has this plant transfer function. Okay, here the goal is to design the controller. Okay, so which should do track this reference input R of t, where R of t having some this is kind of a ramp signal having this slope for duration of 30 seconds. Okay, and steady state value is 300 degrees Celsius. Okay, so generally what we do is, suppose if you see this, you wanted to get 300 degrees Celsius. So generally what we do is, so if you just multiply with zero point 0.3, okay, and apply the final value theorem, where final value theorem is s tending to 0. Okay, so your expectation is you'll get so 1000 multiplied by zero point 0.3 means you'll get to 300 degrees Celsius. So that is the ideal case. Okay. So here if you see the R of T reference, okay, the temperature you wanted to track, okay, from 0 to 30, okay, it is having a the slope of 30 degree per Celsius, 30 degrees Celsius, and then from 30 to 50, it is maintaining 300. That is your reference signal, which we wanted, which you want your thermal control system defined by this G of S to track. Okay, so now suppose if you apply that, if you apply with 0.3, so usually if there is no disturbance, what would happen? So the signal will go like this in this blue curve, and finally it has to match this. Okay, so at any point of time, if you see this error, okay, so these errors somewhere it becomes 0. So this is the error signal. Okay, so this we call it is as a tracking error. Okay, so that we are dealing with the first control system aspect, that is the tracking. So tracking in this sense, you have a reference signal R of t to track. That is your aim. So you have to develop your controller or design the controller to tag that R of t. Okay, so this is the tracking problem. Okay, so then regulation problem is that, so regulation problem is you want your output, system output, to track a reference value. For example, here the reference value in this case is 1. So you want your system to track, so you want your system to regulate to that value. So to reach that value and maintain its value, output value as 1. So that we call it is as a problem of regulation. So tracking and regulation both are different. Tracking R of t could be varying function, whereas regulation, here the R of t is fixed. Here the fixed value is 1. Okay. Here the basic issue is that if there are no disturbances or noise, okay, so your open loop control system will work fine. Suppose if you are getting some kind of disturbance, let's say the disturbance value is 1 in Laplace transforms, that is 1 by S. Okay, so what would happen if disturbance is also added up to the regulation? So you wanted to carry, you want your system to reach a value of 300. That is our problem. Okay, but due to the disturbance added, okay, so this pink curve you can see, so instead of tracking exactly 1, so you are getting a deviation of this much value. Okay, so the open loop systems are majorly the prone to the disturbance values. That is the main disadvantages. So this is the regulation, whereas error also you could see this much of error is existed in the output. Okay, so this is the problem with open loop control system. So particularly when the disturbance is added. Okay, so the third problem is stability. Okay, so the stability problem we have read previously that. So as you see, this is the open loop control problem, where we have R of S, the controller transfer function, the system transfer function, and we have output. Okay, so what is basically the overall transfer function is multiplication of those two transfer functions. Okay, g of s multiplied gc of s. Okay, so now usually what we do to check the stability, what we have learned previously. Okay, so we equate uh, the denominator to 0. Okay, so which gives us the roots. We call them as the poles. So then when can we say that system is stable? So we take this S plane. Okay, and if all the poles are existing in the LHS, LHP, so right hand side of this, left hand side of this, the S plane, left hand side of this J omega axis, then we say that system is stable. Yes or no? Is
Yes,
this
sir.
correct?
Yes.
Stability definition. Okay. So that is how we do. But basically here, when your system is disturbed with when the system is affected with these disturbances, okay. So there is this possibility that, okay, so your poles may, let us say in previous case, okay, so you are adding the disturbance of 1 by s. Okay, so 1 by s is, it means that you are injecting a pole at the disturbance is injecting a pole at s is equal to 0. When s is equal to 0, the pole may not be on the left hand side. Instead, it will be at origin. Okay, so that creates the problem. Okay, so it means that open loop systems are may not be stable all the time. Okay, because of these disturbances. This is the third aspect of the control system stability. The next sensitivity. Sensitivity means, so, you have your plant. Okay, plant has this transfer function g. Okay, suppose if there is the plant has this gain g. Okay, at a particular frequency. So when you are doing this operation, sometimes the plant transfer function may change slight variation of delta z. Okay, so what you are doing basically here, this is the open loop structure. Okay, so you are finding this transfer function. What is the transfer function? Y by r is nothing but gc multiplied g. So let us call that is as overall transfer function L. Okay, so the question is, what if there is a change in the uh, gain of the system? What happened to this L? Okay, this is L without the change in the gain. So what if change in the gain delta Z comes? What happened to L? Let us say here, so L is without change in the gain. So delta L is with the change in the gain. Okay, so now the sensitivity is defined as with this formula. Okay, so the fractional change of L, okay, uh, defined as to the fractional change in G. That means that simply delta L by L divided by delta Z by Z. What is the change we expect in the fractional change in L due to the fractional change in G? So generally we defined the sensitivity in this way. Okay, these are the four aspects. Okay, so one is tracking, regulation, stability, and sensitivity. Okay, so when you consider these open loop systems, okay, because of majorly the disturbances, okay, so you'll not have much control on these aspects. You may not track properly. You may not do regulate your output to the desired value. So the system may not be stable because the disturbance may include other poles. Okay, so the system may not be it may be highly sensitive. What we want is system has to be robust. Okay, so it has to act. I mean, steadily even if there is a disturbance comes into picture. So we don't want our system to be more sensitive. Okay, so these are the disadvantages with the open loop system for these four aspects. So is there any query here on these definitions of these? Because if you see any control system problem, that will be connected with these four problems. Any query here? Any query?
Sir, we have to do problems on
Yeah.
these all formulas and all these properties.
Problems in the sense,
Questions.
uh,
Type
I
of
mean,
questions.
no,
Regarding
no.
what type of questions?
Yeah, yeah. And currently, I'm just reviewing the content of this week 5. Okay.
Okay.
So I'm just explaining roughly. Okay. So if you're having any theoretical questions, you can ask me. So after finishing this content review, next live session, we will do the problems.
Problems in regarding these all topics. That
Yes,
is.
yes, all the topics.
Okay,
Yeah.
sir.
Yes. Okay. So this is about open loop system. Now in the closed loop system. So along with this, so this is the structure we have already in the open loop system. Okay. So now we are adding something called as this sensor connection, this one, which we call it is as a feedback. So in the feedback, what we do generally, we take this output connection, connect this one to a sensor, which will measure the output value. Okay. So then we connect here. So now, apart from compared to the open loop system, so here disturbance is the extra term we have added. Now because we are taking the feedback and feedback is connected majorly with the sensors, sensors are prone to this noise. Okay, so all sensor values may be noisy values they give. So that's why we are adding this noise term also. So basically this from output to the reference input, we call that is as a feedback control. Okay, so is this clear? Any query? So feedback control. Okay, so now if you see here, so we have three inputs to the system. One is reference input, disturbance input, and a noise input. Okay. So what we can do is using superposition theorem, when you give reference input, so you can make d of s n of s 0. So you calculate the first term. Okay. That is nothing but y by r. So similarly, other two also. When you
Sir,
give
why
d
we
of
use? Please explain why you use noise input here.
noisy input, because
Yes.
here you are using sensor to measure the output. Okay, so
Okay.
the sensor may not always be accurate. Okay, so always you will get the noisy measurements. Okay, suppose for example, if you are doing some satellite, you are developing the controller for the satellite. Okay, so always what the output might be the height of the satellite. Okay, so the altitude. Okay, so to measure the altitude, what you do is, so you use the GPS. Okay, so GPS, the values, GPS measurements, okay, they may not be very accurate. Okay, so because of the sensor, because of components in electronic components in the GPS, so there could be a heavy noise included. Okay, so that is one example. The other examples are, suppose you are developing the closed loop controller for autonomous car. Okay, so this is the distance from the front vehicle. Okay, so that front vehicle you will be measuring by using a camera. Okay, the camera, sometimes you may use less FPS camera, sometimes you may use a better FPS camera and a tracking algorithm. So measurements are maybe noisy. Okay, camera view may not be good during daytime and nighttime, etc. Okay, so that's why we are adding the noise. Okay, so now, so for every input R of s, D of s, you can find these expressions. Once you have that, you can calculate this U of s. U of s is nothing but the input you give right after the controller. Okay, so that U of s corresponding to each input. Okay, so could be these terms. You can do the calculations, you can get that answer. This you are doing by using the superposition theorem. So now you can get the tracking error. So the tracking error is nothing but, so you have your reference input which we wanted to reach, okay, and you are getting the closed loop output at this point. Okay, so if you take you are taking the feedback here. So this is nothing but YCL. Okay, this will be your E of S. Error is nothing but R minus Y. Okay, so that's what we are trying to calculate here. So R minus Y. So you have your Y already. Okay, so you have your R. So you will calculate the E of S. So error, this we call it as a tracking error. Okay, so now suppose if you make the other two terms are zero, okay, noise and disturbance. Okay, so now if you do that, the tracking error having some change in delta E of S, so you can find the delta of E of S expression. Okay, you can do those calculations and find the tracking error, change in the tracking error. Okay, so here you could see this expression. Okay, so the for large value of L of S is nothing but open loop control system gain. Okay, so the changes in the tracking error will be very low. Changes in the tracking error is low. So what here we are doing is for the same closed loop control system, we are trying to defining those. We are trying to checking those four problems: tracking, regulation, stability, and sensitivity. Okay. Here in the closed loop control system, so we are checking what is the advantage that feedback is giving. Okay, so you can see this same example. Okay, so the example says that we have this thermal control system. So thermal control system defined with this plant transfer function. Okay, you wanted to track this reference input R of t with having a slope of 30 degree per second. Okay, so for 30 seconds, and then it is stable after that. Okay, so here your control strategy is you wanted to minimize the error between the reference and the actual output. Okay. Then let us say you are using this controller. GC expression is something like this. Okay. Now along with this, you are using the feedback. It means that so the GC expression is so that expression you will use here. G of S is this. So this is the feedback. Okay. So feedback. So whatever the transfer function a particular sensor we use here, so that H of S we will use. So if you substitute them, okay, now you can see this response. Previously, what we have seen is so there is lot of steady state errors existed. So it means that at the end we have seen some 10 errors existed. Whereas here you could see so the error is almost zero, or so it has tracking error is very very less. Whereas in the open loop control system the tracking error is almost 10. Here is almost zero. This is all due to the feedback. Okay. So this is for tracking with closed loop system. So in the sensitivity, similar way, we define in the similar way. So you have this expression, closed loop control system. Okay. Then you define the L, so closed loop gain. So now you are asking, what if there is a change in G that is nothing but delta G? So what kind of change you will get in the closed loop transfer function? Okay. This is the expression. Okay, so now you're going to find this. So if there is a change in G, what is the change you are getting in the closed loop transfer function? Okay, so this is general formula that we have seen in the open loop case also. This is the sensitivity. Okay, see, so here you can see, so this is with the controller, this is the final thing. Okay, so here what it says is, so they are less sensitive to the variations in the plant. Okay, when you compare with the open loop gain. Okay, next for stability. So always remember this derivation. So I'll try to do this derivation once again. Here you could see this is the closed loop system. Okay, here your intention with closed loop system you have reference output Y. So the sensor H, the controller GC, and the plant G. Okay, plant G. Okay, so now here you could see, so what is E? E is nothing but R minus, just a minute. sorry. So here what we are trying to do is, so the error is nothing but what? Error is nothing but reference R minus Y multiplied H. Okay, here you are getting. So this is the first expression. Okay, so our intention here is to find the transfer function Y by R. That is the output by input. Okay, so now from here we could write Y is equal to what? So Y is equal to E, you are giving E multiplied GC multiplied G. So E multiplied GC multiplied E. Okay. So what is basically E is R minus HY. So GC multiplied G. So from here you could take the R out. So you'll get this final expression. Is there any doubt in this?
No,
Is there
sir.
any? Yeah. So this
No,
is
no,
the
no.
general finding transfer function for closed loop system. Okay, finding transfer function for any closed loop system. Okay, in this way we will find. Okay, so now if you look for the stability, okay, so here you could see this is the plant transfer function, this is the controller transfer function. Okay, when you substitute them here you are getting this term 1 plus GCGH. Okay, this term. Okay, so basically, how do we find the poles? We find the poles by equating that to zero. Okay, this is the expression you are getting.
Denominator will be 0.
Yes, yes. So the denominator is zero. Okay, here you could choose your controller C of S and D of S. Okay, in such a way that okay you can make your poles outside the left side of the j omega axis, so that your system becomes stable. That
Stable.
is the advantage with the closed loop system. Okay, it will give you more freedom. Okay, so that is with closed loop system. Then so uh, this is an example, you can follow that easily. So then similarly, in the closed loop system, you have this advantage also. So instead of you assume the D of S is the input, make N of S and R of S both are zero. Okay. So this is the expression we have for the error. Okay. So in this, okay. So if you fix this G of S, okay. So then increase the loop gain here in this case. Okay, so the disturbance will be decreases. Disturbance decreases means you will get this error reducing. Okay, so basically these the disturbance signal you will get in low frequencies. Okay, whereas noise you'll get in high frequencies. This is the difference between these two. Okay, so here the closed loop system advantage is that by properly choosing your GC, you can reject the disturbances at lower frequencies. Okay, that is the advantage closed loop systems. Okay, so similarly, noise I said, so you can take the noise as input and make the D of S and R of S as zeros. Okay, so you can do the same thing with the error. Okay, so basically the noise signals, they will be generated at the high frequencies. Here also by properly varying this L of S, where you can vary this L of S by varying this controller. Okay, so you can uh, do the attenuation of the noise at the higher frequencies. So this is the advantage you get with the closed loop system. Okay, so finally these are the uh, advantages of closed loop over the open loop. Okay, so what are the different advantages? So you'll get improved stability, so sensitivity decrement, okay, rejection of the disturbances, so attenuation of the noise, okay, it could also increase the bandwidth. Okay, so only the issue with the closed loop system is that your system gain might be decreases, and since you are adding the feedback loop and you are doing many calculations, so both the cost and the complexity gets increases. Okay, so these are the main advantages with the closed loop. Are there any queries between
No, sir.
open loop to closed loop?
No, sir.
Yeah. Okay, so next we will see this a proportional controller. So basically, if you see this, okay, so this is the closed loop system we have. Okay, this is the closed loop system we have. In the closed loop system, basically we have reference y, actual output, feedback, the controller gain, and the plant transfer function. Okay, so here the question is, what is the controller gain which you choose? Okay, so in the control system, so you have different options to choose. So various controllers. So the proportional controller, integral controller, derivative controller. Okay, and put together all. So we have PID controller. So for every controller, the system behaves differently. So for example, you start with the uh, uh, I'll skip this one. So you start with the proportional controller. Okay, so you can check the proportional controller. Proportional controller in the sense, so the GC. Okay, so you'll be adding a just number only. Okay, so like some number KP. Okay, so there is no yes term over there, some number. So then you measure your output here. Okay, so you measure your output. So the output will be feeded back. Then you get your error R minus. So error is nothing but uh, R of t minus y of t. Okay, so that error you will get. So that will be multiplied with kp. You will get your u of t, kp multiplied u of t. So that you pass on to this summation, and the disturbance will be added. That signal, this signal, you will apply to the plant, and you'll get your output. Okay, so that is the um then you will see your output. Okay, so then you will find since you want your output to follow this reference signal, so you wanted to see this error e of t is equal to r of t minus y of t. So you wanted to measure this in terms at steady state. Okay, if they both are uh, exactly same, y of t and r of t, you should get your error as zero. Okay, so the tracking error should be
Sir,
zero.
KP
Yeah.
we used as
Mm.
position error constant in steady state error, na KP. Is this?
That depends. That depends. Suppose if you see here, so that depends.
Yes, sir. Yes.
That depends upon the type of the system you have. Okay. So basically, type of the system is nothing but you have your transfer function as n of s by d of s. Okay. So the type of the system is defined with how many poles you have at origin. Okay. So it means that what is the expression for d of s? If your d of s is something like s square multiplied some s square plus 3s plus 2. Okay. Then you say that the type is 2.
Yes, sir.
Okay. Yeah.
Yes.
So depends upon that. These are the steady state errors. Okay. So suppose if you take type as 0. Okay. It means that this is 0. Okay.
Yes,
So
sir.
then depends upon what you give. Your R of t is step input, R of t is ramp, R of t is parabolic. Suppose if your type is 0, okay, so then R of t, if it is step, okay, your steady state error is this much. And if your R of t is parabolic, okay, the type 0 system, uh, it cannot track that. Okay, it cannot track both ramp and parabolic.
Yes, sir.
Okay, similarly, if your system is type 2, okay, so the steady state where error will be 0 for the step input, okay, and for ramp also 0. For parabolic, you'll find the steady state error by using this. So where
Yes.
Ka is nothing but this expression. Okay, limit s is tending to 0, s square g of s. Okay, this you might have done already in the time domain
Yes, sir.
systems. Okay,
Yes.
so based
Yes.
upon that, you can calculate it. So here, basically, the basic point which we needed to note down is when this GC controller is KP, what happened to this ESS that you wanted to see? Okay. So here our intention is the R of t. Okay, we wanted to reach 1. Okay, but the steady state error, that is nothing but uh, E of t is equal to R of t minus Y of t. Okay, that has to go to 0. That has to go to 0. But okay, so it will go to this expression 1 by k plus 1. Okay, 1 by k plus 1. It will not go to 0. It is something like, so you want your system to go to 1. Okay, but you want your output goes to 1, but your output may reach here only. So it means that there is a steady state error of this much. That expression is 1 by k plus 1. Okay, so it means that if you do all the calculations, okay, plot the y of t expression. Okay, so you simply, what I'm saying is take kp is equal to some 3. So g of s is some 1 by s plus 1. Okay, do all calculations. Okay, find take r of s is equal to 1 by s. Okay, do all calculations and find the y of t expression. Okay, you will get some, the y of t will not reach 1 here. Okay, so at a time t is tending to infinity. Okay, it will always stay at some point. It means that your proportional controller always inject, always resulting some steady state error. Is that clear?
Yes, sir. Clear.
Yeah, so that's the main point. So your proportional controller will always results 1 by k plus 1.
K plus
So you
1.
are supposed to reach 1. Okay, but your steady state error will produce 1 by k plus 1. So that's the major point. Okay,
Okay.
so yeah, so you could see here always. So even if you make that kp very large also, okay, so still that steady state error would exist. You can see here kp 1, 5, 10, etc. 20. So in the order of these things, okay, the last one kp is 20. Still that error
Yeah,
is existed.
yeah, yeah,
Yeah.
yes.
So that's the problem with the proportional controller. But the advantage with the proportional controller is that when you keep on increasing the k, okay, it will try to bring your output to near to the reference value. Okay, for that sense, it will help you. Okay, so now came back to the same example. So you wanted to reach 300 degree Celsius. Okay, if you use the G of S is this. So now GC, if you use KP, okay. So what it does is basically it will try to reduce the tracking error. Okay, it will try to reach that 300 degrees Celsius, but it will incur some steady state error at the end. So here you could see here. Okay, so here it is injecting, it is resulting a steady state error of 10. Okay, so the 300 is this line and actually is this line. Okay, so it will reduce the steady state error. Okay, the tracking error reduces, but still you have this steady state error, ESS. Okay, that's the problem with the proportional
Control.
controller. Okay, next. So always you have this error. Okay, so what you can do is you can add these poles to change the behavior, which we also call them as the dominant poles. So that is proportional controller. Next, we will see what is integral and derivative controllers. Yeah. So integral controller, basically I said, so the proportional controller is resulting steady state error ESS. It is resulting a steady state controller ESS KP. Okay. So in integral controller, what we do is basically, so this G of S, Okay. So this g of s we will replace with integral of e. That means here, so you have your y, output is y. You have reference is r. Here e is nothing but what? R minus y. Okay. So this integral controller, what it does is it takes the integral of e up to that time. It means that it will be adding all the previous errors till time t. Is this clear?
Yes, sir. Clear.
So that is integral controller. You could see here. Okay, so u of
Yes.
t is nothing but ki, some integral constant multiplied by the initial time to t e of t. Okay, so basically the integral is necessary. Why? Because what is our intention here? We wanted to make this error to zero. Okay, so
Yes, sir.
let us say at time t, if y and r, if they are same, what will happen to the error? If
Then,
y at a time
y,
t,
yeah. Then E
okay,
equal to 0.
so e becomes zero. But what is u? U is nothing but what? U is
Integral
nothing
error.
but u is nothing but this error itself.
Yes, sir.
Okay, if e is zero, sorry, if I use just ki only here, okay, so if I use the just e only, okay, so if u is equal to e, okay, so now here the error becomes zero. If error is zero, what does it mean? U also zero.
Yes, sir.
So when R and Y are same, okay, you'll get error as zero. If error is zero, U also zero. If U is zero, the input which we are giving to the plant is also zero. If plant input is zero, Y also becomes zero. It has no
0. Yes,
meaning.
sir.
It has no
Yes, sir.
meaning. Okay. So that's why what we do is instead of keeping E, we take the integral of E. We take the integral of e. So in that sense, it will be the previous error will be added all the time. So what do you mean by integral basically? So if you have any curve, okay, so let us say this is t, okay, so this is f of t. What is the integral f of t? So that's the area covered by this one. Okay, so that never be zero. Maybe your error at a particular time is zero, but error from 0 to TF is not zero. Always that is nothing but the area. Okay. So that's why instead of direct error, we'll take the integral here. Okay. So that's the importance of this term. Is that clear?
Yes, sir.
So
Clear.
now when you take the Laplace transform, you will get what is the integral of the Laplace transform of integral e of t is that is 1 by s. Okay. So
Yes.
this will be your controller transfer function, GC of S. Now, when you include this one and do the calculations and finally find the expression for y of t and you have r of t, you get e of t, which is nothing but r of t minus y of t. Okay. Then find e of s applying the transfer function. Then find ESS, which is nothing but Laplace limit s is tending to 0 s e of s. Okay. So what is this basically? This is nothing but this is due to the final value theorem. Okay. You're trying to finding the
Yes.
steady state error.
Yes, sir.
Okay. So when you do that, you will get zero error, zero tracking error. Okay. So previously using proportional controller, some tracking error was existed. Now this will result to zero tracking error. So that's what this expression says. Okay. So you're applying this is the overall area. Okay. Instead of zero error, you will be using the overall area. Okay. So then you are finding the E of S, this expression. So you take the limit S is tending to zero, S E of S. Okay. So that will make the total, the tracking error, steady state tracking errors to zero. Okay, so that's the advantage with the integral controller. Okay,
Yes, sir.
so then you could also see this disturbance case. Okay, so you apply some disturbance and find the transfer function. So take the disturbance as some 1 by s. Again, do the same calculations and find y of infinity. Okay, you will find that y of infinity you'll get 0. That is nothing but the output due to disturbance. Okay, it means that the integral controller has the ability to reject the disturbances completely. Okay, it can do both tracking and disturbance rejection perfectly. Okay, so that is the advantage. Okay, so again, same example. So what you do is you replace that GC of with the integral controller and
Yes, sir.
check whether you are reducing this error or okay. So GC of S total transfer function. So characteristic equation. Okay. So now you could see here the response is close to 300. That is our aim. And the steady state error has reached zero error. Okay. That's the advantage. Okay, so next we have this derivative controller. So in the derivative controller, basically what we do is, so in place of GC, okay, we take the derivative of error. That is nothing but E dot of T. So if you take the Laplace transforms, you'll get KD multiplied S. Okay, so the problem here with the integral controller is, okay, so let me explain here. You could see here the so you have missed this one. So these overshoots are very high. Okay. So the overshoot is nothing but here this much overshoot. Okay. Even sorry, this much overshoot. So 300 to 350. So what is the overshoot? Almost 50.
Yes, sir.
Correct? You wanted to reach 50, 300, but your first peak went to 350. So almost to 50. So overshoot is very, very high. That's the disadvantage with the integral controller. So the derivative controller will handle that overshoot issue. Okay. And also it improves the closed loop stability. So basically that overshoot is defined with something called as the transient response. Transient response is nothing but what? We have two responses, transient and steady state. Okay. Transient means was what? So when you get the response, okay, so the response in shorter times, starting times, and the response after a long time. So these are called the transient response. These are called steady state response. Okay. So the integral controller will not handle this transient response properly, whereas the derivative controller will try to reduce this overshoot. Okay. And provide the better transient response. Okay.
Sir,
So
transient means when it is changing the with
yeah,
respect to time, the
yes, yes,
response is changing, and steady
yes.
state when the signal is stable, then
Not exactly.
most probably,
So we define with respect to the time. Okay.
yeah, yeah,
Suppose here you have total 250 seconds. So during starting times when you are oscillating, your system is oscillating. Okay.
yeah.
Till let us say here till 100 seconds. So generally we call that is as transient. And after that, the system tried to get stabilized after
Yes.
some time.
Okay, okay, okay.
So that we call as steady state. Okay. So
Yes.
the derivative controller will handle these situations easily. Why? Because so here you are taking E dot. E dot is nothing but what? dE by dt.
Yes,
Okay.
yes, yes.
That is nothing but d by dt of r of t minus y of t. So that is nothing but r of t dot minus y of t dot. It can handle both how my reference signal is changing, how my output is changing. Okay. What is the deviation between these two? Okay. So that will be handled by the input due to the derivative signal. Okay. So that's why we said it is proportional to the rate of change of the system error. That error is depending upon both reference and actual output. Okay, so that's why the transients will happen only during starting times. That will take care of this. At the same time, E dot is nothing but what? Basically, derivative is nothing but what? So when we say x dot, what does it mean?
dx by
So
dt. That
dx
is,
by dt. So that is nothing but x of t plus 1 minus x of t. Correct?
yes, sir. Yes, sir.
So
Correct.
by change in the time. Okay. So basically, what does this means? So you are you are looking one step ahead with the present step. Okay. So here E dot means it always anticipate what is coming front because of this value. Okay. So what is coming front? What is the error I'm going to get? Because we are
Okay.
looking for the e of e t by dt. Okay, so that is the advantage with the derivative controller. Okay, so it always anticipate the behavior of the system because so because this e dot, by knowing e dot we will know how the slope of the error is changing. Okay, so the basic advantage is that since you are looking one step ahead, it will always prone to the noise. That is the disadvantage with the uh, derivative controller. Here, by looking at the anticipatory behavior, it will try to reduce this height, the overshoot. It will not make the system to reach that height very easily. Okay. So that is the advantage with the derivative control. Now here in this table, you could see easily. Okay. So first with the P controller, P controller, basically it reduces the steady state error. Okay. Sorry. First, it reduces the, sorry, it reduces the rise time. Okay. So this is first point. Okay. It reduces steady state error to some extent. Okay. Sorry, it will create the steady state error. It will reduce, but still it will not make the steady state error to zero. Okay. Now, integral controller, it will make the completely eliminate the steady state error. Just a minute. Okay. Integral controller, it will eliminate the steady state error and it will increase the, you can see that it will increase, it
Yes,
will
overshoot.
overshoot. Okay. So the derivative error, it will decrease the overshoot. Okay, improves the stability. Okay, so it will create some kind, it will inject some kind of noise. Okay, so this is how you could see one by one. Okay, so what you do is when you design system, so you want everything. Okay, so what you in that sense, what you do is you don't use the only one controller at a time. So instead, you will use mix of controllers. Like sometimes you will use PI whenever your requirement is to reduce only steady state error and reduce the rise time. Sometimes you use PD. You wanted to increase the rise time. So sorry, reduce the rise time, and you need your transient stability more, right? When you need all these things, you will also use the PID. Okay, so that is the final controller. Okay, so something like this. First, you have this PI controller, which will have both P term and integral term.
Integral. Yes, sir.
Yes, so you'll get the both the advantages. Okay, so it can reject the disturbances. It will reduce the steady state error. Okay, so you can see the example. So uh, here, so the steady state error is zero. So the rise time is better one. Okay, so then you can have a PD controller. Okay, so where you'll use KP and both the derivative term. Okay, what it does basically is it will add a zero. Here PI, it will add a pole. Okay, so it basically the because of this derivative term, the system anticipates how much overshoot is coming up. Okay, it will take action accordingly. So it improves the damping of the system to reduce that overshoot. Okay, so we have these two terms. Okay, you can visualize it how it is happening. Okay, so then you'll have to have all the advantages. So you could have the uh, P controller, integral controller, and derivative controller. Okay, so you'll get all the advantages like stability, tracking, disturbance rejection, and improved transient stability also. Okay, so if you want, you can take the MATLAB and plot the responses. You could easily see this in plotting for the same example. Okay, so I think it is already 6. I think I gave the enough overview. Okay, so
Yes.
yeah, so uh, now it is time for the class test. Okay, so let me give you a question. I'm writing the question here. Okay, so let's say we have this is two controller GC, and this one the gain is 1 by S plus 1. Okay, so this is Y, and this is R. Okay, so we have error. So let us say feedback is 1. Okay, so this is your problem. Okay, now tell me the steady state error. Tell me the steady state error of this system. Okay, we can write the problem, find the error. So this is E, find the error, take the, apply the final value theorem and tell me the steady state error. Okay, so you can write it and send me the email. Yeah, so we
Sir,
have 10,
give
10
me
minutes to
some
do.
time. I will draw the circuit, sir.
Yeah,
Please
yeah,
zoom
yeah,
the
yeah, yeah.
picture. Sir, we have to find
Steady state
CSS.
error. Yes, yes.
Acha.
Okay, so I'm closing this call. Okay, so you have
Yes.
10 minutes to send. So right now time is 6. You can send me by 6:15, 6:15 or
Okay, sir.
6:20. Okay,
Yes, sir. I will do that problem and
yeah.
take this.
So you can mail me. So
Uh, I,
Chakravarti underscore J. The email is I'm writing here in the chat. So Chakravarti underscore J at the rate of study.iitm.ac.in. Okay, you can take that. So thank you. We'll meet on Wednesday.